Go. Hello and welcome back to Calculus 1, section 4.6 on linear approximations and differentials. So this is one of those sections where we learn it just in case. Let's say a solar flare hits the Earth and just fries all of the electronics everywhere. We need to rebuild that stuff. So you have to know a method to calculate ln of 3, sine of 5, right, by hand without any calculators because they're all fried. It actually happened in Canada a few years ago, where the solar flare took out the entire electrical grid for days. So it's not out of the realm of possibilities that we can at any point in time go back to Stone Age very quickly. That means no running water, no sewage, no fridge. Forget about entertainment and TV. Everyone is like, oh, I would die without TV for like 3 days. No, you're probably going to get infected and die of some terrible disease because there is no sanitation. So this section will teach us how to compute these values to great precision. And we will then, in differentials part, we will learn how to approximate the change. So we'll see that. So we start from linear approximation. So how much is the square root of 15? Well, there are certain things that you can do. You know that the square root of 9 is 3, and the square root of 16 is 4. So square root of 15 has to fall in between, and because it's much closer to 16 than to 9, so let's say, 3.8. Or 3.9. Even closer, right? So this is your guess. And it's called an educated guess because it's obvious that if 15 falls in between 9 and 16, then 3.9 falls between 3 and 4 and much closer to 4 because 15 is much closer to 16 than to 9. Now, what would be the cool way to actually figure this out? If I have my function f of x square root of x, and I say that I'm interested in computing value at 15, what is the close value that it's easy to compute? Well, clearly 16. So 16, value 16, will have a tangent line. So this is tangent line. And look at this area here. This area says that computing 15 in tangent line is very close in result as computing 15 in square root of x. Because look at the y values. The red and black are pretty much the same height. So this is the trick. Instead of calculating square root of 15, we are going to find the tangent line at the closest best point, which is in this case 16, and then compute 15 in a tangent line. We do the entire thing without a calculator. So let's do that. I have my f of x as a square root of x, and the point of interest is 16, because that's closest perfect square to 15. So we know how to find the tangent line, right? We take the derivative, and then we find the slope, which is, in this case, 1 over 8. Then we find the y value, which is f of 16, which is square root of 16, which is 4. And now I have 16, 4 as a point, and I have slope to be 1 over 8. So my tangent line y equal mx plus b. I need to find b. So y is 4, m is 1 over 8, x is 16 plus b. 4 is equal to 2 plus b. B is equal to 2. So the tangent line is y equals 1 over 8x plus 2. Now, here is the $1 million thing. Square root of 15 is approximately equal to the tangent line calculated at x equals to 15. So, square root of 15 is approximately the same as 1/8 times 15 plus 2. So how much is 15 divided by 8? Well, it's 1 point, and then you have 7 left, right? So that's another 8, 7, 5 plus 2 to give me 3.875. So we found that the square root of 15 is this. Now to check, I'll use the calculator to compute square root of 15, and we get square root of 15 as 3.872, well, 3.873, because the next one is 9 and then 8, so on, so. Wow. In our calculations, we never use the calculator. Yeah, I used the calculator at the end just to check my answer that I got by hand, but prior to the blue line, we did not use calculator once. Not once. And we calculated that the square root of 15 should be about 3.87. And the calculator says 3.87. You see this? And if you're looking at the third decimal, then they disagree. This is really cool. We can compute stuff using the basic tangent line calculation, and all of these things from before, the ln2, the ln3, the ln5, the sine of whatever, cosine of whatever, we can use these things. Let's calculate ln3. No, actually, no, compute, approximate. So what are the specs? Well, function f of x is ln x. And what's the a? Value that it's close to 3 that we should use. What's the value? Close to 3. That works nicely with ln's.
1.
Anything better? E is about 2.7. And ln of E is 1, so it's nice and easy calculation. So let's go find the tangent line. F of x is equal to 1 over x. Therefore, slope is 1 over E. Now, the y value is ln E, which is 1. So we have E1 as a point. Y equal mx plus b. Y is 1. M is 1 over E. X is E plus b. So we have 1 equals 1 plus b. B equals 0. So the tangent line is y equals 1 over E times x. So the ln3 is approximated by 1 over E times 3, which is 3 over E, which is 3 over 2.7 approximately, which is 30 over 27, which is, when you cancel by 3, 10 over 9, which is about 1.1 repeated forever. So we calculated that ln3 is approximately 1.11 going forever. Calculator? You go and you punch in the ln of 3, and you get that ln3 is approximately 1.0986, 122, and so on. It's like 1 cent away, 1.2 cents away, right? This is insanely good. Now, prior to all of your technology in terms of calculators and cell phones and tablets and computers, these were the methods used 100 years ago, because you need ln3. What is it? There's no technology to compute that. And just 50, 60 years ago, engineers walked around with the books called log tables. It's a book that all it has is tables of values inside. So you go on page 1, it has ln of 0 is undefined, ln of 0.1, ln of 0.2, ln of 0.3, and all of these values are in the book. The entire book is only log tables, trig stuff, so value for sine of 15 degrees, 15.1 degrees, 15.2 degrees, 15.3 degrees, right? The entire book just reference, then they had slide rule, and they had all of these other things. What they did not have are calculators, tablets, right? And they created calculators, tablets, computers by looking at these log tables. Now, the log tables come from calculations like these. And the story goes that captains on ships were the ones mostly responsible for these calculations, so that, because they had a lot of time on their hands. I mean, it takes you, it's only wind, right, to power your ship from England to US, let's say. What do? You have like one execution a day, and the rest is just free time. So you sit and you calculate these things all day long. Now, it will be a cool thing, I hope, to see a tangent line formula in one equation rather than having the full procedure for this. So we call that linearization. function Lx, and that's f of a plus f prime of a times x minus a. So this is the formula. We call this linearization equation, but all it is tangent line at x equals a. So it's a one-liner for your line. And I just want to jump into the homework and pick up an example so we can use this formula. So linear approximation. Let's do ln of 1 plus x. Oh no, I just did ln. Should we do a cosine function? Compute. No, compute. Approximate. Cosine of pi over 4. Okay, we can do that. How much is pi divided by 4? So we need that decimal, and it needs to be always in radians. So pi divided by 4 is equal to 0.785. So this is approximately cosine of 0.785. So that's what we're looking for. No. I read the problem wrong. Hold on. They want us to approximate cosine of 0.8. There we go. That's much better. Cosine of 0.8. Now we know that cosine of pi over 4 is root 2 over 2. There we go. And pi over 4 is 0.78. What did I say? 7854, which is close enough to 0.8. Close to 0.8. Nice. So now we find the tangent line. Now I'm going to do everything in one line. L of x is function computed at a, but a is pi over 4. So that's going to be function, so cosine of pi over 4. Plus the derivative of cosine is negative sine, so negative sine of pi over 4 times x minus pi over 4. So pi over 4 is my a value, right? One that it's nice to compute, and it's very close to what we actually need, which is 0.8. So now L of x is equal to square root over 2 over 2 minus square root of 2 over 2 times x minus pi over 4. So this is the equation. You can go ahead and multiply these things and get it, but no one cares. Because our cosine of 0.8 is approximately the same as L computed at 0.8. So now we have square root of 2 over 2 minus square root of 2 over 2, 0.8 minus pi over 4, and whatever we get here from this calculation, it will be. Now, is this easier? Of course not, because you take the calculator and you just punch in cosine of 0.8 and you're done, right? Now I have to take the calculator and compute all of this nonsense, which is actually worse. So this looks like it's worse, and it shouldn't be, right? When it becomes being worse, you abandon it and you use a different method that it's easier. Well, we can compute at least this. Calculator gives me that the cosine of 0.8 using the above calculation is approximately equal to 0.696, well, let's do 7, so three decimal places, it's fine. And now I'm going to do calculator. You make sure that your cosine is going to be in radians. So go to mode, it's radians, good. So cosine of 0.8 is pretty much the same. So if I round it, so I'm gonna go back to the decimal, and the previous decimal was 77. Okay, so 6969 on the calculation, and this is 6967. So you see that the first 3 digits over here match, and then there is 2 off. So these methods are really good. Really good. Okay. So that's our linear approximation. And what linear approximation does is approximates the value. You don't want to compute ln3, fine. Find the tangent line and approximate ln3. So find the tangent line, and each one of these was find tangent line, find tangent line. We are approximating the value by using the tangent line calculation. So the numbers that you want to compute are not computed in original function, but they're computed in a tangent line, and a tangent line is an easy calculation because it's a linear line. So that's the first part of the lecture. The first part of this lecture is to approximate y value of the function rather than compute it exactly. Say you don't have the calculator handy, so you can calculate things differently. Now, the second part of this is differentials. And what the differentials do is they approximate change in function value, which is the output. Again, is this something that is crucial for our survival at the moment? No, it's not, because we have computational power to calculate exact change every time. So, what is the exact change? It will be delta y, which is y2 minus y1. Right? So, to give you an example, calculate the change in y for y equals 3x minus 1 when x goes from 1 to 2. Right? This is extremely simple, right? And it's going to give us the exact answer because it's easy to calculate. So y2 is 3 times 2 minus 1, which is 5. And y1 is 3 times 1 minus 1, which is 2. So the exact change is 5 minus 2 equals to 3. So that's what it's meant by exact change. You calculate the value and then you subtract the other value. So you have, right, your input changed from one number to another, which causes the change in the output from one number to another. And they are obviously related. Now, differentials do not compute these things exactly, what differentials do is they go and approximate this change. So to develop the formula for differential, we write the function y equals f of x, right, from pre-calc, and then we take the derivative of it. On the left-hand side, you have Leibniz notation dy dx. On the right-hand side, you have modified Newton's f prime. So you have function is equal to itself, right? Function is equal to function, y equals f of x. That's the notation from pre-calculus. And then on the bottom, you have two different notations from calculus. One is Leibniz, one is modified Newton. All I need to do now to create the differential is to move dx to the other side. So dy equals f prime of x dx is the formula for differential. So that's the differential. What do I do with it? I use it to approximate the change. So I say that my delta y is approximately the same as dy. They are not the same. So this is important right here. It's important. On the other hand, delta x is equal to dx, and that's x2 minus x1. That's your input. So input is the same, but output is not. So now I can create this final version of the formula, if you want to say so, where it says that change in y is approximated by dy, and the dy is equal to f prime of x delta x. So this would be the boss equation, because you are stating that you are approximating the exact change by the differential, and differential is equal to the derivative times delta x instead of dx, because delta x is actually the change from x1 to x2. Now this is used in the design of things, and I'll mention some of them later. Let's take a look at approximate the change in volume of a sphere when its radius changes from 5 to 5.1 feet. Right? So we have a sphere. Don't need to be dramatic. So we have a sphere, and we have its radius r. Radius r starts off as 5 and goes to 5.1 in feet. Approximate the change in volume. Again, can you find the exact change? The answer is yes. Use your volume formula for sphere, plug in 5.1, then use it again to plug in 5, and then just subtract two numbers. That is going to be your exact change. But we don't want to do all of that work. Instead, we are going to say that the volume of the sphere is 4/3 pi r cubed. You got to know this either way. And now, I'm just going to say that your y is v and your x is r, so you are not lost when we switch these variables out. So now, the dv dr is equal to 4 pi r squared, from where dv is equal to 4 pi r squared dr. This equation here is your differential. That's your differential. And now I have all of these. I know that the dr is the same as delta r, which is 5.1 minus 5 equals to 0.1. Now, this part over here, I'm going to write this in blood. This is new minus old. Because the values could shrink. And if they shrink, well, you need a negative sign. Right? So, we either have the growth, expansion, or shrinking. So, if this was... let's say this sphere is a weather balloon, all right? So you are deflating it, right? Well, then the radius is getting smaller. So in that case, you will have 5 minus 5.1 for a total of negative 0.1. Now we have positive 0.1. And all I need to do now is to plug this in. So change in volume, exact one, is going to be approximated by dV, which is 4 pi, instead of r, I have 5 squared, and then this is 0.1. So how much is this? 5, this is 31.4. Because 5 squared is 25 times 4 is 100 times pi is 314, and then move 1 decimal point, so 31.4. So, answer. When radius changes from 5 feet to 5.1 feet, the volume increases 31.4. Volume increases about 31.4 feet cubed. Because the radius changed, the volume changed. The radius went up, the volume is going to go up for the positive amount. If I'm deflating the balloon, the radius goes down, the size of the balloon is smaller, less volume in a balloon, so in that case it would be negative. So you just have to be careful which one, right, which one you have. Now guys, this plays a very big role in design of items and things that are around us. And some of these you use very frequently. Some people also even more than, right? Have you been on a train ever in your life? And then have you been on a train in the winter in opposition to the summer? Have you noticed anything about the noise that the train makes along the way? So unless you're always with the headphones and you have like no knowledge of the world around you, if you are on the train and you actually hear the noises that the train makes, you will hear the tak-tak, 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 all the time. Why? Especially in the winter, is much noisier than in the summer. Well, what happens with things when they heat up? With objects, they expand. I see you making your, right? Do they expand double their length or so? No, they expand very little, but they do expand. So when you heat objects, they expand. Now, train rails are very long, right? And not that fat. They're very long. So the expansion for those is going to happen much more in length than in the width, right? So now, when you lay them all together and you connect them to those wooden planks, if you put them close what is going to happen in the summer when they expand? They're going to, right? Because the only way they can go is they can go in, right? They can't bend on sides because they are nailed to those wooden planks because they need to be parallel because of the wheels of the train, right? So so here I have 5 of these markers all connected together. So as I push in, you see what happens? As I push in, because they expand, and this whole thing falls apart. Now you can find pictures, black and white photos of old train tracks that have all these rails bent and popped out. Why? Because there was no gap between the rails when they installed them. So there was no play for these rails to expand, which is why the noise is bigger in the winter than in the summer, because in the summer, when they expand, they close the gap, and the train just goes over it, and the noise is minimal. In the winter, tak 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 tak, tak 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 tak, because the first part of the wheels goes over it, then the second part of the wheels from the same car goes over that gap. Every time it creates noise, right? So there's that noise. Another one, bridges. You go to any of these huge bridges that we have around, or going to New York and so on, you find that zigzag, right, mesh on the bridge, right? You drive over it, and there are a few inches of separation. And if you look through it, right, you see all the way down. So the bridges are done in sections. Each section will expand in the summer because it's hot, and there's close off, and and you're driving over it. And then in the winter, right, they don't go 7 miles apart, so you just fall into the river, right? These are all, they are carefully calculated by the structural engineers and civil engineers that are working on bridges and making these calculations. They know exactly the properties of materials they use and so on. So they know how far apart they can make them so that, you know, the bridge will not have the same issue as train tracks. So the bridges are not falling off their own accord, right? Because it's 100 degrees outside. Design of tires and all of these things. As you increase in the summer, you will find a lot more exploded truck tires on your highways than during the winter, because extra heat from the, it's 100 degrees outside, plus the heat of the friction between the road and the tire, right, heats tire more, and then the tire expands, right? So there are all of these things, and then there is the one that connects pressure of the tire with all that. So there is all of that, right? Another design that, so we talked about trains, well, train tracks. We talked about bridges. Tires. Now, here's another one. So, and in the old times, when I was growing up, there used to be something called a CD disc. It carried music on it, right? You guys don't know what that is. So these CDs were discs. That was a CD player. You put that in a CD player and it plays music, right? Now you have the same thing for a Blu-ray, right, disc for movies. Well, this was just music. There was no picture to it. All right, so what is the principle on which this works? You pop the disc inside, and then there is a laser that reads the data. What happens with the object when you shine laser to it? It heats up, right? It heats up. So what? You're heating up this disc with laser, so what? It expands, exactly.
That's what they get, like a little bit of room extra when you put on the tray.
That's just the method to hold it. You have to worry about that. That's mechanical engineering. Ship that off. How about electrical engineers? What they have to worry about? How precise is the laser? It's very precise, right? You can store a lot of data on these disks. The CD disks used to be about 650, 700 megabytes of space. And then you have the DVDs, right, that were...
4.7.
I'm sorry?
No, I think it's 4.7 gigs for the DVD.
Yes, and then you have the Blu-ray ones with 20, 25 gigs on them, right? They're the same disk. It's very precise. That laser reads, right? Now, imagine that there was no device that measures the temperature and calculates the expansion and all of this stuff, right? Everything that that's all you're gonna get. Everything that is on the disk, because it will keep skipping, right? It will keep skipping all the time. The old designs for cars were not that much heat sensitive. I remember my first CD player in a car in 90s. That thing, as soon as the outside reaches like 86, 90 degrees, it was already, it was just going through, chopping up everything because of the design, right? So your linear track on which the laser is that moves back and forth, right, needs to account for the expansion of this, and that is calculated real time, because when you pop the disk in, it's not heated up yet, right? It's cool. The temperature sensor is not kicking in to tell if there is expansion so much to make a correction for it. So it just reads it off of the, right? And then as the temperature starts kicking in, because you've been listening now for this music for let's say 30 minutes already, right? Anytime you pop these disks out, they're always warm, right? They're hot. That means they expanded, right? They expanded. So you have to account for the temperature, and you have to do it real time. You can't pre-program, because it's not going to be the same change in heat in these things if you are playing the same music disc in the same music player in January and August. It's completely different set of, because you also have to add the temperature of the ambience to it, because it will be, right? My discs that are in the car, right, they're going to be in the winter. They're going to be maybe 40 degrees. And you pop that in a CD player. Now it's 40 degrees. It's going to take laser much longer to heat that disc up from 40 degrees to whatever the problem for these materials. By the way, that's where the material sciences kick in, right? To know the expansion for particular type of plastic and stuff like that. So all of these things, guys, come to design, and you cars, engine block. How does your car work?
Pistons.
Yeah, pistons. What is that? Pistons, right? You have a cylinder, and then on the bottom of the cylinder, you inject gas. Gas is what? Dead plants and animals, right? From hundreds of thousands of years ago. That's oil. So you get gas and oxygen, and the spark plug makes the spark and explodes it. The explosion pushes the piston pushes the rod, turns it a little bit. You have 4 or 6 or 8 of these, right? Constantly working in the succession, and that it turns the shaft, which is translated through the rest of the engine to turn the wheels, turn the alternator, and everything else, the air conditioning, and so on. So would you agree that there is expansion when you are constantly exploding things in the air? Why is the engine hot? You are making controlled explosions in that thing all the time. All the time. So each one of those chambers is a chamber that houses these explosions. And every time the explosion, right, goes off, then the gases from the explosion push the piston up to give the power for the car, and then all of the stuff that it's the gases and everything is sucked out, and that goes to the exhaust outside of the engine. So a lot of friction, a lot of noise, a lot of wasted energy. We talked about the cars being only about 25% efficient, which means when you fill your gas tank with $40, 30 is wasted, and 10 is what drives you from, for the entire tank, $10 is what drives you from place A to place B, runs your music, air conditioning, and everything else. Which is why electric cars are so damn expensive and better. 98% efficiency on Tesla, which means that 98% of the electricity that you put into the battery of that car is used to drive you around, in contrast to 27% efficiency of any car that actually has engine. So you see that that's 4 times efficiency. 4 times efficiency is 4 times savings in money, plus no oil change, no engine parts to be broken. You only have a battery and 2 motors, right, for each one of them. So technically,
Is it an expensive battery?
Well, yeah, but when you consider why and what it is, right, then it makes sense, right? It makes sense. You have something that is 4 times efficiency, and you are saving more than 4 times the money, because electricity is cheaper than the gas, right? That's one. And then also at the 4 times efficiency, so you are getting more than 4 times value. Now, when you compare a regular gas-powered car in a better category, say you take Audi, BMW, or something that's $40K to buy, one of those introductory models, compared to Model S, which is $80K, that's only twice in price, but more than 4 times in efficiency. So there is that, right? So it's actually, and the argument that it's green and that's nonsense, because all of the electricity is coming from nuclear plants, right, that are producing nuclear waste, and it's coming from also thermal plants, right, that burn coal. So the pollution to get the electricity, right? They say, oh yeah, but there is no exhaust on the, well, yeah. Instead of me directly polluting by having the exhaust come out of my car because I put the gas in it, right? Someone else burned coal or gas to make the electricity, which I imported in, right? So it's not green. Electric cars are not green at all. But are they environmentally friendly? Hell yes, because they're 4 times more efficient. So that means that 4 times less pollutants are introduced for the same amount of driving that you would do. So are they 100% green? Hell no. They are just better. Until we figure out fusion. Once the fusion is in, then we have then whoever has the gas power car should be shot. Because in that case, right, that would be insanity to have a gas powered car with the fusion, with electricity that is produced by a fusion, because fusion produces 0 pollutants. You put in hydrogen on one end and you get distilled water and helium on the other. So, right. So that's so that's what we have. So guys, this is what we have. Part one was approximating the value, and the part 2 with differentials approximates the change in value. So I'm going to give you one more problem for the change to try. We can talk about, let's say, circular cylinder, because circular cylinder is like for the pistons for the car, right? So you can do that. Approximate the change in volume. So again, dV is delta V. For the cylinder, it's a terrible picture of a cylinder. There we go. That's better. See you next week. And then we have a radius is going to be 20 centimeters, and the height is the one that changes from 12 to 11.9 centimeters. So you better come up with a negative result over here, right, on the volume, because it is getting smaller, right? Be right back. You got the negative number?
Yeah.
Good. So we start with the volume, which is pi r squared h. Radius is constant at 20 centimeters. So we actually have 400 pi h as a formula. H is the only thing that is changing. So we have dV dH to be 400 pi. dV is equal to 400 pi dH. Delta H, which is equal to dH, is 11.9 minus 12, which is new minus old, which is negative 0.1. So dV is 400 pi times negative 0.1. So the change in volume is approximated by dV, which is negative 40 pi centimeters cubed. Now you can go and say pi is 3.14 if you want more decimals, but it's not necessary. If you really want to check this, you will go and calculate exact volume at 11.9, then you will calculate exact volume at 12. When you subtract the two, you will get a number that is close to this one. Each one of these problems is just a different formula. Now, to finish off this lecture, we can also use differentials to approximate numbers indirectly, because you have your number that you want to calculate, and then linearization will give you another number, and then there is a change right there. So we can use differentials also to approximate numbers. So let's calculate square root of 95. You want something else? Square root of 95? Whatever, right? Square root of 95 is equal to the question mark. So we can use linearization, but we can also use differentials. So my f of x is square root of x, and what I'm going to do is I'm going to take x value, which was 95, and change it into 100, because that's the easy number to compute. So I immediately have that delta x is equal to what? 100 minus 95, yes. Which is 5. Okay. So y is equal to square root of x. So differential is dy is 1 over 2 root 100, which is x, 2 root x dx. So dy is equal to 1 over 2 times square root of 100 times 5. Square root of 100 is 10. So this is this 1/4? I think.
Yeah. Yes.
1/4, right? Because it's 10 and then 2 and then 2 times 2 is 4. Good. So now, how much is my delta? So what is my square root of 95? Square root of 95 is square root of 100 minus 1/4. That's what it is. So It's 10 minus 1/4, and I get 9.75. So that's what my differential says. Now, what is the calculator? Calculator says the square root of 95 approximately, and then we punch that in the calculator.
Yeah. Close.
Square root of 95. 9.74679, so that's 8. Right? Exactly, right? These methods are amazing. I mean, we have technology today, right? But that technology had to be, right, made. So, there are methods of calculation, and a lot of the, good old methods of calculation are lost by now because we just have calculators and people don't learn them anymore, right? Well, that's approximations. Bye.